This lesson is about properties of logarithms. Now, before I even get into it, I just want to remind you that a logarithm is essentially an exponent. In our previous lessons, we have looked at this concept because previously when we were introduced to logarithms, we said that if a to the x equals y, so if this is true, then, this was in our definition of it, log base a of y is equal to x. And again, I'm just reminding you then, x here is an exponent. But then that same exponent is here and it's equal to a logarithm. So a logarithm is an exponent. So we should expect logarithms then to behave like exponents. And today we're going to make the connection about how they do behave like exponents, but how we should notate it on our paper. Before we get into talking about logarithms, we're just going to kind of go through some of the properties of exponents. There is a product property of exponents that says x to the m times x to the n. So I point out that even though the symbol's not here, this is multiplication. They've got the same base but different powers. And when that's true, we get x to the m plus n. So it was multiplication, but we end up adding exponents. And you probably intuitively know that by now, even if you wouldn't have been able to write down that definition rule, because x squared times x cubed is equal to x to the fifth. We add those exponents. Now, the quotient rule has to do with division then. So if you have x to the m over x to the n, just like multiplication became addition, division becomes subtraction. If we had x to the seventh over x to the third, then we would subtract those exponents and it would equal x to the fourth. Now I'm going to go ahead and point out here, because I know this is going to come up later, if it were x to the third over x to the seventh, there are two ways of writing what that is, but one of them is that just again we follow subtraction, and 3 minus 7 is negative 4. But that is the same as 1 over x to the fourth. And you can understand that because if we have more of them on the bottom, then we're going to end up with them on the bottom. So a negative exponent really just means it needs to move across the fraction bar. And keep that in mind as we're going along also. A power property is if you have something that has an exponent and you raise that to a power. So on a power to a power, this is where we actually multiply those exponents. So if we have x squared raised to the third, this is going to give me x to the sixth. So here when we multiplied, we actually added. And when we're raising it to a power, we actually multiply. It's kind of like a sliding scale. It's one thing back. Now the property of equality is sometimes just called that one-to-one, and it's kind of an if-then. And I'm not going to try to write an entire sentence in here, but what we know is that if we have x to the m is equal to x to the n, then that would indicate that m was equal to n. And this is double-headed because it goes both ways. If m is equal to n, then you could take a base and put it on both of them. So like if I had x to the y is equal to x squared, what that would tell me immediately is that y has to equal 2. And on the other hand, if you know y is equal to 2, then x to the y would equal x to the second. So a logarithm is an exponent. So on our next slide, what we're really looking at is these same exact properties, but they're written different because they're written in terms of logarithm. So what I would point out again is that here, where we had a product, because that's m times n, then we end up with an addition. Now do note that we end up with a log in front of each part of that. So on the left, we only had one logarithm, and we end up with a log on each part of it when we separate it into addition. This over here on the example, since this is 9 times x, we want to separate that into addition, but instead of log base 3 of 9 times x, we get log base 3 of 9 plus log base 3 of x. Now, it's not necessarily clear right here, but the reason we learn to break them apart like this is because then sometimes they will simplify. Like log base 3 of 9 is equal to 2. And we couldn't say that this is equal to 2x. It's not. But we can take this and say it's equal to 2 plus log base 3 of x. So learning to break them apart will, in the long run, help us simplify things. Here we have a division symbol. And division becomes really subtraction, but you put a log with each section. Now in our previous thing, a power to a power, we ended up multiplying those. So right here, power to a power, I just multiplied those powers. But again, a logarithm is a power. So what happens here is that this p moves essentially like to the front. And this power gets multiplied to the logarithm, which is a power. So that's the way it gets written right here. So if you see an exponent within a logarithm, you move it to the front. On our one-to-one property, if you have the same base, and we had an x to the m and an x to the n on our other one, but if you have the same base on both logarithms, then actually the arguments, the part you're taking logarithm of, end up being the same. And you can see over here on the example, what that's going to allow us to do is essentially kind of get rid of writing the logarithm and just say, oh, these both have the same base of 8. So that means the part we're taking log of, which is called the argument, is equal. So 3x minus 4 equals 5x plus 2. And then we can solve that equation with algebra from previous sections. All these examples and definitions, they go both directions. We can take two logarithms that have addition and we can write it as a single logarithm. We'll be able to go both directions with this. I certainly didn't cover all of them, so here's just a few more of the ones that we use a lot. Now the change of base formula, if you've got the TI calculator, you're not really having to use this formula because you can just go into math and find that option for a log base and put that in. However, it's going to be helpful to you to recognize that both ways of writing this are equal to the same thing, and I have an example where we'll see that. And then other properties. Now, 3 of these properties have something very strong in common, and that is that you're going to see matching letters here. Now, on the last 2, we could say they have the same base. Like this logarithm has a base A, and this exponent has a base A. Here, the exponent has a base A, and the logarithm has a base A. But we also see it here. And we have some very interesting things that happen, and the reason they happen is not because things cancel exactly, but yet it's not going to mess you up if you think about it that way. It has to do with just that definition. What this log base A of A means is A to the what equals A. Well, that's going to be the 1. This one means A to the what equals 1. Well, anything raised to the 0 power is equal to 1. This one actually works because if we bring this exponent to the front, then I would have an x right here, and it would say x times log base A of A. But again, we've already seen that log base A of A is 1, so x times 1 is x. It's a similar sort of a rewrite here. A to the what is equal to A to the x. Well, A to the x is equal to A to the x. But what you can kind of think about is, oh, it's that other one. Like here, if you thought about just marking those out, well, we'd say it equals 1. Here, that's going to go away, and we're just left with the x. And here, that stuff goes away, and we're left with just the x. But it's not exactly a cancel, so that's not the right mathematical term for it. Okay, so this is what your homework's going to look like. Express as a single logarithm, and if possible, simplify. Now, there's a couple of ways to do something like this, and I'm not going to lie to you, your calculator will be able to handle those. But what your calculator is going to do is immediately simplify. So if you needed to express it as a single logarithm, which is kind of funny because I know this is one logarithm, but this is what the instructions look like on the homework. You want to take and say, okay, well, 81 times 27, and that's 2,187, log base 3 of 2,187. And then simplify becomes 3 to the what is 2,187. But I'm going to actually kind of use a cheat here. I know that 81 is 9 times 9. 9 is 3 squared, so that makes this one 3 to the 4th. This one I also know is 9 times 3, so that's going to make that 3 to the 3rd. Which means I could say then by combining those that this part is log base 3 of 3 to the, using my exponent rules, I can add those, 3 to the 7th. And now notice that I have the same base here. So based on what I saw on the previous slide, this is just equal to 7. Your calculator will do it if you use that log base. But here I'm going to say, okay, well, 8 is 2 to the 3rd. 64 is 8 times 8, so that's 2 to the 3rd times another 2 to the 3rd. So that's 2 to the 6th. So this is essentially then log base 2 of 2 to the 9th. And again, you can see that those 2's, the base of the logarithm and the base of the exponent are the same. And this one is equal to 9. Now again, the reason that technically works is because we could take this 9 and move it to the front, and then log base 2 of 2 is 1, 9 times 1 is 9. Now, your calculator cannot handle these, so you have to know how to apply the rules. So express as a product. That's where we're going to say, oh, this exponent needs to come out here to the front. And so this will be 3 times log base b of t. Now on this one, it doesn't look exactly like I have an exponent. So what you do need to keep in mind, so I'm just going to kind of put an asterisk here, is if you have a root of anything, so let me just put a scribble, how about that, to represent anything, and it's raised to a power, then this is equal to that anything raised to the p over r. So the power becomes a numerator of, it's still a power, but it's in the numerator, and the r ends up being in a denominator. So when you think about it like that, if I say that this is 4 to the 1st right here, then I can rewrite that as ln, and do keep in mind that's an L. When you're doing your online homework, it may look like just a capital I because of the font they use, but it's an L. So this is ln of 4 to the 1/4 based on what we put right here. And then this 1/4 will move to the front. So this is 1/4 times ln of 4, and that would be your answer. It's not asking for a decimal, it just wants you to write it like a product, and that's 1/4 times. That's a product. Now the difference, you've got to remember the divide becomes subtract. But you do need to write the log with each part. So I have log base t of m minus log base t of 8. And I know it's longer, but that's the answer. Over here, this one, log base a of 76 minus log base a of 13. In this particular slide, it told us exactly what to do. Express it as a product, express it as a difference, express it as a single logarithm, simplify. But sometimes it just kind of wants you to do it all together. So some of your instructions will say express in terms of sums and differences of logarithms. Now I put a little asterisk here because it doesn't have that in your homework instructions. But when it says sums or differences, it actually wants you to also use products. So those exponents are going to end up in front of the logarithm. This really makes the problems longer because you have to rewrite a log with each part of it. So a lot of times we just call this expanding a logarithm. it's helpful to just kind of do it all at once because nobody wants to write log over and over and over. So one of the things I often do is just kind of make a little note. Every place I have a multiply, which is here, here, and here, will become an addition. Now I will have to put a log with each one. And every time I have an exponent, I'm going to move it to the front of that term's log. So if you look at this one, then it's going to be log base A of 6 plus, see I had my little plus written there, and I'm just going to always write that log base A of x plus, now this one I've got to bring that 5 to the front, so that's going to be 5 log base A of y plus, and this 4 is going to come to the front of the z log, so that'll be, oh, I almost forgot it right after I said it, log base A of z. This one had 1, 2, 3, 4 factors in that product, so I ended up with 1, 2, 3, 4 logarithms. But I did need to bring those exponents to the front. So this one, I have 3 factors. Since they're all multiplied, each one of them is going to end up with a plus. And then these that have exponents will end up moving to the front of the logarithm that goes with them. So that's not, it's not just going to be 3x, but this just kind of gives me a reminder as that my eyes move to where I'm looking, okay? So I'm going to have log base A, and then I see this line, I move to right here. 3 log base A of x plus, the 2 is going to move to the front, 2 log base A of y plus log base A of z. It is true when we've got a quotient that 2 is being divided by 3, 2 is being divided by x cubed, or that result is. So rather than do it like in one huge piece and then have to distribute, the fastest way you can do this is just keep in mind that anything in the numerator will be a positive or addition, and anything in the denominator is going to be subtraction. So this one's going to be positive, and then I'm going to have to subtract this log. And even though this is a multiply, because it's in a denominator, that negative really gets distributed to it. And then this is going to move to the front. So all the ones in the denominator will end up being negative because the negative in front of the entire thing gets distributed. So we have a positive ln of 2 minus ln of 3. Also minus 3 ln of x minus ln of y. Now here I have a root, so based on my previous notation, we just want to rewrite that root. So that one is just log of, now this is b to the 7th, the little root out here is a 2, so that's going to be b to the 7 over 2, and c to the, well, this has an understood 1, so that'll be 1 over 2. So this is what I'm going to use as I rewrite my logarithm as an expansion. Here, these will both end up being positive, so I have log, but now the power will move to the front of the log for each one of those. I'm going to have a 7 over 2 log b. Now, it didn't show a base. That means it's an understood base of 10, but I don't need to write it either. And then I have plus a 1/2 log c. And then our last one over here. Again, I've got a division. So anything that's on the numerator is positive or plus. So I'm going to end up with a plus between those logs. Anything in the denominator, because we're going to it's all subtracted, we're going to end up distributing that to both of those, and then the 2 will go to the front of this one. So this one is log 5, it's base 10, plus log a minus log 4 minus 2, because of that exponent, log b. And of course, once we learn to take it all apart and make it really big, we're going to work backwards and put it all back together. So as we go the other direction, the notations we'd want to make is that if you have an exponent, it's going to become a power. So this exponent here will also become a power. Multiplication is going to become times, and we won't have to write both logs. So this one is just a single log, and it is n to the 1/2 times m to the 3rd. So here, I'm just going to mark it out. 1/2 is going to go with the x. 4 goes over here as an exponent to the y. 3 goes here. Now this subtraction means I'm going to end up with division. And this means I had multiplication, and I will not write all those logs again. So I'm going to have a single logarithm. I do know there's division, so I'm going to draw a fraction bar out here, and then I have x to the 1/2 on the top of it times y to the 4th. And then in the denominator, I have z to the 3rd. On this one, we have a 1/2 here, and this becomes divide. Don't write the extra log. So I have log of a to the 1/2 divided by 2. We put them in a single logarithm. They always get shorter, so we call this condense. Condense the logarithm. This page is a practice of just applying what we talked about on same bases. So look at these closely. The base of the logarithm and the exponent is the same. Base of the logarithm and the exponent is the same. These are the same. These are the same. Now the other two are written with the base of the exponent first, but again, the base of the exponent and the logarithm is the same. When that happens, that's just a little miracle for us because those are our favorite ones. They're so easy. This is equal to 3. This one equals the absolute value of x minus 4. Simplified. We didn't get an exact answer, but we know that's what it is. This one equals, I bet you've got the hang of it, 4x. This one is 2,713. This one is the square root of 3. And this one equals 4x minus 3. This lesson is really about applying those properties and laws of logarithms and not doing a lot more with them, but this is a tool that we're going to use a lot in our next lesson, because in our next lesson we will apply these rules as we are solving equations. That finishes up this lesson. Don't forget, send me and ask the instructor if you have any questions.